Okay, hi guys. So in this lecture, we'll be taking on some examples of simultaneous equilibrium. So let's get started. So suppose we have a first equilibrium as A gaseous converting itself into B gaseous plus C gaseous. So initially, let's say, or let me write it out the final equilibrium state only. Final equilibrium, let's say it has A minus X moles. A obviously being the initial moles of A gaseous, and at equilibrium we will have X moles of B and X moles of C. Now simultaneously in the same vessel, one more reaction is taking place in which B is reacting, rather B is decomposing at equilibrium to convert itself into D. Okay, so let's suppose it was 2x, so it would be A minus 2x and X moles of G. Okay, and the formed 2x moles of B at equilibrium actually dissociates Y moles, so it produces 3Y moles of D, and it dissociates Y moles of itself. So at equilibrium it would be having 2x minus Y moles. Similarly, both of the concentration, or rather the number of moles at both the equilibrium, should remain consistent, hence I am also adding 2x minus Y here. Okay, so as the reaction is happening in the same vessel, so we can see that the B formed from in first equilibrium number 1 is used as reactant in equilibrium number 2. Okay, so total moles at equilibrium would be consistent 2x minus Y moles for B, X moles for C, and 3Y moles of D. So finally we can say that 3Y moles of D formed when both equilibrium simultaneously established. Okay, now we'll look at example number 2. Where we have, let's say, 2 moles of A, or 2 moles of A converting itself into Bg plus 2 moles of C. So in here, let's say at equilibrium, what is the state? So at equilibrium, let's say we have A minus 2x moles of A, so we will have X moles of B and 2x moles of C. Now this was the first equilibrium. Now simultaneously in the same vessel another equilibrium is establishing in which 2 moles of B gets dissociated into 3 moles of C and 1 mole of D. So now you can say that at equilibrium what will happen here is, from the X moles which were initially present from the first equilibrium, let's say 2Y moles of B dissociated to form 3Y moles of C and Y moles of D. So as moles of B at this equilibrium is X minus 2Y, similarly we have to reflect it here also to have the consistency in the same vessel, and as 3Y moles are still more produced of C, and initially from the first equilibrium 2x moles were only there, so we'll add 3y to the first equation from the second equation, and 2x from the first equation to the second equation, because the number of moles in the same vessel of the same product should remain consistent at equilibrium all the times. Okay, so this is how we look at it. Now let's see equilibrium from a kinetic approach. Equilibrium constant, rather not equilibrium constant from kinetic approach. Okay, so let's say we have an equilibrium wherein A gaseous is converting into B gaseous plus C gaseous. So here what is happening is, from the kinetic point of view we can write that the rate for forward direction is, let's say, kf, and rate for backward direction is kb. I hope or if you don't know what is the rate of a reaction, we can just write it like this, that rate of a reaction, we'll obviously be seeing this in our coming physical chemistry lectures, maybe not in this series but in the next coming series, but we'll definitely look at it. So rate of a reaction is actually dependent on, proportional to the concentration of reactants. Okay, in other terms we can write that rate of a reaction, we remove the proportional sign and replace it with kf or other k, which is k is nothing but the rate constant multiplied with reaction concentration of reactants. So in this case we are saying that rate for forward direction is kf and rate for backward direction, in which the reactants would be b and c, is kb. Okay, so now let's say in the same reaction we have bg plus cg. Okay, so in the same reaction, let's say the initial concentration was, let's say it was having a mole concentration as a, initially they were both 0, and let's say what is the concentration at time t. Time t is any random time, it may or may not be at equilibrium, it is during the span of reaction. We are just screenshotting the reaction at any point t and we are seeing the concentration. So let's say it was a minus x, x and x, and let's see the concentration at equilibrium. So what would be the concentration at equilibrium? Let's say we are denoting it with xc, xc and xc. Okay, so now we come to some of the terms here, that what would be the rate of disappearance of A. So disappearance of A would be nothing but what is the rate of forward direction and what is the rate of backward direction. If we know the rate of forward direction and if we subtract that from the rate, or other, if we subtract rate of backward direction from the rate of forward direction, we get the rate of disappearance of A, because a product A would be getting disappeared only when it is getting consumed to something and it is reverting back from something. Okay, so rate of disappearance would be how much A is going forward or dissociating into products, or disappearing or converting into products. So rate of disappearance would be rate of forward direction, which is this one, and minus, you have to subtract this incoming back A, because it is again forming more A and we are talking about disappearance, so we have to subtract this term. Okay, so minus dA by dt, d is the concentration of reactant A, and we are having negative sign to show the disappearance. We are talking about disappearance would be rate of forward direction minus rate of backward direction. Okay, now we know that rate of forward direction is nothing but rate constant of forward direction multiplied by concentration of reactant for forward direction. Concentration of reactant for forward direction would be nothing but concentration of A, minus rate of backward direction would be rate constant of backward direction, which is nothing but Kb, and the reactants for the backward direction. Now please pay attention here that the reactant for backward direction would be concentration of B and C, because the backward direction goes from right to left. In that case, when going from right to left, the reactants would be B and C. Okay, this is minus dA by dt. Now let us talk about the rate of appearance of B. Another term here, rate of appearance of B. So rate of appearance of B would be nothing but, this is B, how much B is getting formed from the reactants, and minus how much moles of B is getting reverted back to form reactants again. Okay, so rate of appearance of B, which we can denote it by dB by dt. B is the close brackets, B is the concentration of B, which should be equal to Again, rate of forward direction signifies that A is dissociated into products and B is one of the products. Hence, rate of appearance of B would be equal to rate of forward direction minus how much B is getting converted back into the reactants, which is A. So we have to subtract this term from the incoming term. So incoming term is rate of forward direction. Rate of forward direction is nothing but we saw Kf times concentration of A, and rate of backward direction is nothing but Kb times concentration of B and C. Okay. So please remember this, that this is the rate of forward direction, this is the rate of disappearance of A, and this is the rate of appearance of B. Okay. And we can say that at equilibrium what will happen is nor A would be disappearing and neither B would be appearing. So we will be saying that minus dA by dt would be 0 and dB by dt would also be 0. Okay, so we can say that this implies 0 equals to rate of forward direction minus rate of backward direction, which is same for both the cases. Hence rate of forward direction is equal to rate of backward direction. Okay, what is the rate of forward direction? So we just saw that the rate of forward direction would be nothing but Kf time concentration of A, and rate of backward direction would be nothing but Kf time concentration Kb times concentration of B and C. So we can write that this implies that Kf upon Kb would be equals to concentration of products divided by concentration of reactants at equilibrium. This is talking about at equilibrium state, and this should be equal to Kc, which is equilibrium constant. Okay, this equation is at equilibrium. Okay, so this gets us to the same formula which we have discussed before, that but we got one more analogy, that equilibrium constant would be equal to rate of forward direction, or sorry, rate constant for forward direction divided by rate constant for backward direction, or nothing but Kf upon Kb. So with this we come to the end of this lecture. In the next lecture we'll be seeing non-standard states in which reversible reactions takes place, and then we'll be seeing phase equilibria. So till then, good luck and goodbye.